Thanks, Carla, for your introduction. Um, um, and it's really nice to be here in Zurich. And I just wanted to introduce myself. I'm actually also part of a media and design laboratory, and a lot of work has been done in collaboration with the team members there and the students with teaching and research. So just wanted to thank them for this body of work. And the title today is called Deep Architectural Form Towards a Machine Understanding of Architecture. The talk will highlight the potential of AI and deep learning in architectural design in bridging the multidimensional aspects of architectural form, in emphasizing the role of creative methodologies and computational tools in crafting future designs. I just wanted to start off by this photo of, so this image of Zurich Main Station in 2008 is actually by BSA, the architectural organization of Switzerland. They asked all the architects in Switzerland to donate provide their competition model, this wide massing models, which is kind of critical element in architectural competitions in Switzerland. Now is the microphone working? Or actually, oh no, sorry.
We're sorry.
No, I'm like, just wanted to make sure everything is, oh, it's better now. It's working, yeah, okay, so. and I also wanted to mention in Formulations, a book by Andrew Witt, which is presented as the both conceptual and formal archetypes are the models of the architect, where the collections of models opens a range of formal aspirations and methodological strategies. So architectural form and models are deeply interrelated, as models serve as a crucial tools for visualizing, experimenting with, refining, and not just physical characteristics of design, but also enabling architects to transform conceptual ideas into tangible structures. So traditionally, the role of form in architecture has evolved significantly. Like what began as a form giving with architects as the sole creators has shifted to form finding, where technology and computer-aided systems enable deeper exploration and analysis of form. Now with the machines capable of learning from vast data, we are entering an era of form searching, where these tools offer unprecedented contributions to the design and research processes. So actually, I just submitted my thesis yesterday. So this is like kind of a summary of that work, and also like past 5 years of work, which is completely outdated with the technology that we have now. So I just wanted to say that in the beginning. And so basically, they're operating at the nexus of form and data in architectural design. I'm going to share these 4 projects from teaching and research at our lab, talking about the 4 dimensions of architectural form and exploring a new way of looking at form with machine learning as a dynamic, multi-dimensional entity influenced by various factors in architecture. So those are collection of form, imagery of form, and language of form, and anatomy of form. The first collection of form actually deals with the figurative dimension, expanding the tangible and geometric properties, emphasizing the formal and volumetric attributes of architectural entities. So that data set we were investigating is actually a competition data set. And I don't know if you guys remember this competition in 2015, Guggenheim Helsinki competition was kind of one of the biggest competitions, and kind of controversy because it never got built. So this is the view of the website they had, to showing all the projects. And of course, as a human capacity, we can actually, this was their tagging system that they used to search the projects. So as a human, there's a limitation on how we can actually categorize this, this kind of a lot of data that we have. And in terms of a formal understanding, you can see on the left that these are like pretty much how we can comprehend, like straight, curved, circular, kind of a primitive way of kind of categorizing this data set. And the actual data set that was used was the Swiss competition data set. And the Swiss competition system is very well organized, as some of you might already know. And this particular collection was selected for various reasons. And one of them was the consistency in the data set, and also this the regulation that they have to make it all consistent, and also the data that is available in the jury report is one of the assets that was used. And during the competition, you can see kind of example of these boards that ranges from 3 to 10 boards, for certain requirements, such as like 1 to 200 drawings, 1 to 20 facade details, as an example. And a lot of times you can see this kind of a jury scene where a lot of conversations happens around this wide massing model. So even though that people actually, we look at the boards and drawings and concept, a lot of conversations tends to happen on this abstract model because it's actually the kind of a representation of the project itself. So this model, massing model, became kind of a key driver of this research, where not just looking at the formal characteristics of this model, but also the competition data. And within this formal, just by the abstract form, we can learn a lot of these things by looking at the complexity of the geometry and also the context. And also, when it represents from wide massing model into a certain kind of a data format, we can learn a lot of things more than what we think. And this is an example of like one competition and all the submissions of the massing models. And the ones that were actually used for the experiments is actually the ones who got the prize winning, so who won some prizes. Because only those data were available in the jury report, like all the plans and sections to reconstruct this massing model was a part of the process. And you can see kind of on the bottom, you can see we collected basically, we collected 600 3D massing models from 63 school competitions past 20 years. And then on the top, you can see kind of the examples of it. And this was done manually, which took a lot of time. But we can see also the integration in the whole process together, because nowadays you also have to submit like a BIM models in the competition system, so we can see kind of how we can actually use these data sets for future research. So these were done in a kind of tedious way of reconstructing them, and also, of course, we also have to think about how actually back in the day, I mean, like nowadays you can actually use any number of points in the machine learning process, but 4 or 5 years ago, it was very limited. So the points, we transformed these massing models into inspired by the G code, and then getting points out of all these lines and the curves. And at that time, we used 2,048 points for each massing models. And here you can see kind of the transformation of the samples of the massing models into these points. And we use the unsupervised machine learning 3D adversarial autoencoder, and basically to encode these points, and then also to reconstruct these points. And during this point, we get this kind of we call it latent points, where we can actually spatially arrange these forms and then figure out the formal affinity. So you can see kind of the process of how these points are learned and then reconstructed. And this is the method that we use, as also like Andrew suggested, with a lot of mapping. This is a very critical point, because this is how machines read these forms, and then as a human, we have to actually kind of understand how the machines actually look at these forms together. In this process, one thing that we thought about is, because we're only using 600 models as data set, when these models are actually created for like thousands of data sets of cups and airplanes. So as an architect, we always have to think about how we can actually meaningfully use these models in an architectural context. And if you only have 600 models, you question it, is it going to work, right? Like, so we try to like kind of optimize this process of creating something called architectural point cloud, meaning like compared to before using a uniform point cloud, that is, points are distributed equally. We try to think, as an architect, can we find a way we can actually better to assist the machines to actually learn these models. So that's why the architecture point cloud was created. And then you can see how, by slicing in a different ways, we can actually kind of give focus into certain aspects into the formal quality of the models. So here on the left, you can see the reconstructed model of the uniform point cloud. And on the right, you can see kind of taking a slicing in the horizontal way. So this actually represents that we can already kind of hint at it, that where there is no points, it means that there is a flat surface, right? So this kind of things that we kind of thought in the process for how we could actually help the model to learn. And also in the different factors too. What does it mean by having an actual scale of the model versus actually normalizing the scale to 1 to 1 to 1? Does this matter to machine? Does this matter to human? Like, what's the difference? And there's also a way of how the point cloud was constructed, in like a horizontal model or vertical model, or like what happens if you orient the models in a certain direction so that they're all parallel to each other, what does that mean in the machine learning? So these were kind of part of the investigation, and then using a Tissany or UMAP to understand the formal affinities, how machine understands. So this is kind of a back-to-back human and machine collaboration, and also this research also taps into the traditional way of archiving architectural data, architectural competition. So this is one of the Swiss competition, Swiss architectural competition archiving system, and it's very like it's just like posts, right? Like, and then if you do more, you can actually kind of categorize it in a geographical location, different types of programs, different types, which year it is or which area it is. So like there's certain things that we can the traditional has been done before. So the new way of kind of thinking is actually looking at this kind of a spatial mapping and then affinities of the formal qualities of the models as a form. We can look at into a new way of looking at architectural archives. So this is basically, we create a platform where we can actually input the machine learning results, and then also the data set, also the metadata, not just about this formal affinities, but also like the actual traditional, the data set that we have goes also on here. So we can actually look at all these things in a comprehensive way, in a transcalar way, but looking at through the formal affinities of models. So all these metadata is still included in the part of the archive, and also looking at how these models are deployed out into in the formal affinities. So here on the right, you can actually also see a different way of organizing. I will show a video of this, and here you can also see like different colorization could emphasize on the different formal clusters or different types of competitions, or what are the rankings. And so you can actually look at this archive in a different way. So here I'm just going to show kind of a quick demonstration of the interface, so you can actually see how things are deployed. And you can actually organize like all the point cloud learning in a different point cloud system is also embedded in to see the differences between different point clouds. And also you can see like, you can also like search by different architects also, like if you select, let's say Zurich, which is a Zurich architect, you can highlight where the Zurich's architectural projects are in terms of for the schools. So here you can actually you can also look at the formal, like the similarity between the models, not just in one competition, but across different competitions. So it actually provides a lot of different way of reading these competitions all together holistically, not just one specific competition. And the gradient also represents how closer the formal affinities are. And here you can see kind of the one competition that there is an outlier within this competition. The rest of it looks very similar, but there's one outlier that has kind of different types of formal. And you can also see that who won, who in this process. Also, this tool is capable of creating a new models, basically by interpolating different forms. That was actually in the learning process. And I mean, the quality of the form is not as precise as the original one, because it's only using 2048 points. But you can also see, but you can also starts to mixing unlimited number of kind of forms together. So by here you can see, by choosing one form, you can actually see the in between of these two forms, and you can also start to add more forms to it. So to look at how, by basically generating more forms. So here is the third one that you can add actually. So you can see control in a way to create forms that are go in between. And this research is keep going, it's ongoing. And now that the text with the large language model, the text is used in the jury report is combined with this process. So by fine tuning the large language model with the 3D model and a text, we can actually kind of create a system where we can actually have a dialogue with this system about each specific form itself. And the next step is the part that I was talking about. By typing these kind of formal qualities, we can actually create the 3D forms basically using these data sets. So that's the next step that this research is going. And the next project is about imagery of form, and with the introduction of GAN, we used a lot of images like 3 years ago. But as images for architects is very important because it's used as a precedence, but not only helps designers to jumpstart their designs and overcome their inertia, but also grounds the resulting design in a geographical context and gives a cultural relevance and meaning to it. And the data set that we used was the Swiss alpine cabins. We basically scraped 6,000 images on the web and then downloaded 6,000 images of photos capturing the 150 Swiss alpine huts, and then had this process, created this process of generating these images, but in a way that we can actually curate. The idea of the creation was about how we can actually, how can machines understand Swissness. So a lot of data, I mean, a lot of the students actually basically, they curated their data sets based on what they think the Swissness is. And here you can see kind of the examples of the GAN images that was chosen by the students, and analyzing them in not just in a image, but also in a mathematical or in an architectural in definition, and also collecting this kind of a catalog. But the most important thing in here is how we can actually translate these 2D images to 3D images. Because this is also when the creativity happens, how we interpret the 2D images into 3D. And of course, like perspectival machine has been, I mean, we've been using as an architect how we can represent this 2D to 3D. But with the GAN, it's a different game, because there's also these models are actually trained based on this kind of a human photos in the beginning, and humans, I mean, the face has actually a very structured system with the eyes and nose, but as an architecture, I mean, for architecture is very complex. So how we can actually navigate this world of 2D images with GAN into a 3D world, and you can see. Sorry, all the videos are not working at the moment, so I don't know. Okay, so, and these are some examples that, one of the sample of a data set that was, I mean, the generation of the images that was created, but you can kind of see that they're all perspectival views. So what we try to do in this research is how we can actually connect with the machine on this kind of a perspectival mindset that we have as an architect. So all the data set that had a frontal image was all deleted, because of course if you click, I mean, choose the ones that have more views, more facades, you can actually has more information than just the flat images itself. So all the the flat images was eliminated, and also with the machine clustering system, you can actually, by the results of the images that was created, you can actually cluster these with the by different perspectival views. So you can kind of map out these images are actually looking like from this view. So here's kind of a zoom in. And from this, we can actually also cluster in a way that, I mean, this is the clusteration in Ticiny that I show you as a representation, but you can also see this family of refuges that gets created within different clusters. So these becomes kind of a way to interpolate as a, so the idea was with this interpolation, the idea was choosing the family of refuge, Kaban, and then as if we interpolate it as if we're actually turning the model itself from 3D. So that was kind of the idea of choosing the views, different types of perspectival view. That's why the clustering of different perspective views was important, to choose the images that goes across this cluster. And here you can just kind of see how you can kind of almost like as if once you kind of turn around the model, you start to see this kind of hidden part that you don't see in the one image to another image. And here you can see other examples where this is chosen kind of the same system of looking at different perspectives. So from this, as a human, we can actually understand what could happen in between by turning these views. And of course, at the end, we also have to construct this in 2D to 3D. But as an architect, we also has been traditionally and historically, we've been building 3D objects from 2D images. And one of the idea that was used was the inverse perspective projection system. By Brooke Taylor. So basically from a perspectival view that shows three sides, we can actually get all the informations about the facade from a single point of view of image. So this was actually used to create a grasshopper tool where we can actually put this image in and actually choose the point of vanishing points, and also actually input all these kind of architectural details that goes onto the image, and then transform that into, this is a process on the left where choosing the vanishing points and then going through the script, you can actually kind of automate this process of getting the facade, 3 facades from the image. So this was reconstructed into 3D, and this was a system that was used to create these of 3D forms that actually from a GAN image. And of course, it's important that these images actually carry all these kind of knowledge that we have of environmental and this kind of cultural resiliency that we have in the Swiss Alps. So all these image that actually holds this kind of data that can be employed into the form itself. So as students, they also interpret these images into actual facade details. Here you can see the examples. The third exploration is actually on basically on the language form, which is happening right now with all these large language models and image, text to image. So basically, wait, what? Oh, yeah. So the third chapter actually deals with the semantic dimension that utilize. So the third chapter actually is on semantic dimensions, basically utilizing the formal language-based generative AI to develop a formal vocabulary and embed semantic richness into architecture. So as an architect, we've been using we've been using the language in order to in our design processes, and we make it into kind of domain-specific formal vocabularies. Here you can see Richard Serra's 84 verbs and 24 possible contexts, and also other examples of Farshid Musavi's functional form, FOAs of phylogenetic trees that shows the classification system on their projects, how the morphological characteristics of it, and also other kind of verbs that was used in the process of designing. The book that the data set that we use is actually, I don't know if you guys have seen this book, but it's 1,001 building forms, sketches done by Francois Blanchard, called Silas. And basically this images was used into actually a fine-tuning process of a stable diffusion. So with the 1,001 images, and then the formal domain-specific formal vocabulary was created on this 5 different categorization, from entity to shape to direction and operation and effect. So these 5 words was used, and then this is kind of the prompt that was used to regenerate these images. So this process, 1,001 images, was tagged also manually to explain the formal characteristics of these single images. And it was done by myself because it's also Francois Blanchard's mindset of the sketches, but it's also my interpretation of how these formal characteristics are explained. So if I start to kind of divide the work, you start to lose like the consistency in how you tag these images. And even for myself, like one day later, I forget what I tagged. So it's like it was a very kind of process that was kind of tedious tedious to do. And this is samples of kind of the images that was generated, which is very similar to the original images. And another tool that was created is actually looking at this kind of statistical reading of how these words are connected. So the stronger the lines are, actually there's a strong affinities in how words were connected, how many times the words were connected. So we can assume that kind of if there's a less connectivity, there's going to be more variations in the image generation. And if there's a stronger connectivity, you can kind of guess that there's going to be a reproduction of the original image again and again. So here is a zoom in of this kind of system, and here you can see the results of testing the original image with the text. So on the top, you can kind of see it was able to kind of reproduce the words of the original image to the new fine-tuned model. And then on the bottom, you also kind of, it's not perfect, but on the bottom, since it's a fine-tuned, you can start to like pick up those images where there's a courtyard. So like if you type a courtyard, it will start to remember the courtyard that was learned previously from the large language model and shown again. So here's some other examples that basically using 5 different words to recreate this original image. So sometimes there's more variations, and sometimes there's more consistency in terms of the generating the images again. And then by using kind of the matrix system, you can actually start to hybridize these different vocabularies that was used in training. So which is actually quite hard as a human to kind of just imagine what could actually look like if you start to think about these vocabulary with this vocabulary and this vocabulary. And so this matrix can actually expand further to almost infinite combinations of this formal combination, characteristics of combinations. Here's some zoom-ins of the examples that was generated with the vocabulary. And then you can also inverse this process of, by just putting the sketch into it, you can actually, machines can actually read what could be the formal characteristics of this image. So at that test, we tested, it showed kind of a very good result of actually machines can regenerate that the vocabulary that was used if they were not able to successfully predict what the vocabulary used, that they still predicted kind of a similar verb that was actually described in the image. So this idea of kind of fine-tuning is very important as an architect with all this large language model, because it's really hard to generate something that you really want to do. That's why there's like a prompt engineering now. So this is kind of a power of how, as an architect, we can fine-tune to domain-specific data set this large language model, which is also impossible to just do it with only 1,000 images. And now it's capable, we can capable of using the large language model to combine this kind of two different domains. And the idea is that like we can actually generate now with the models that are out there, that we can actually generate the text with the 3D. So hoping that we can actually move into this step from using the text into 3D. And another thing that was kind of using this stable diffusion, the idea of the textual inversion is also interesting, because this is also, as an architect, it's hard to reproduce certain things that you want and by just typing it. You have to type in like endless trials to kind of get what you want. But with the textual inversion, you can actually just kind of choose like 3 to 5 images and basically embedding this knowledge into the large language model. And so here you can see kind of different steps of, first one is the data set, and the second one is actually reproducing that data set with the embeddings, and also how can that be in the kind of architectural context. And here you can see kind of examples of students, they did the idea of conceptualizing this data set with the different elements, architectural elements, or aesthetics, or kind of tectonics, so that they can test in from the top to bottom is actually increasing the complexity of the context to generate. So the idea of in this research is also kind of how you can actually hybridize existing structure. This was a Kyoto matcha, traditional house of matcha, and how you can actually use this technique to use like these embeddings and also in painting to actually kind of create a design where you can actually hybridize, or like adaptive reuse of a glimpse of kind of going into that direction of adaptive reuse in terms of images and language. And the final chapter is actually on the anatomy of form, and this dimension actually is it's basically looking at the use of parametric computational tools in combination with the graph learning to model and visualize kind of complex flows within the built environment as a novel way of looking at architectural form and design. Traditionally, like the discourse of flow in architecture is much tied to the relationship between diagrams and architecture. Flow and bubble diagrams manifest biological analogy with circulatory systems and organs, and how they have become the basis of the rational approach in architectural design. The rationalization of architecture into flow plan diagrams allow for clear objective to taken into the design process and become the image of modern organism. The computational geometry allows for the extension of the concept of flows into architectural language, manifested in the continuous expression of malleable surfaces, enabling a new way of organizing flows through architecture. The flow becomes a formal expression that can be materialized and experienced. So these developments contrast the two distinct architectural flows. First is the flows as a rational and scientific means, and second as a formal expression. So kind of Mobius house by UN Studio kind of represents this kind of the dual natures of flows and incorporate them into a design process. So in this process, we created a tool inspired by the Sankey diagram, which is originally developed to quantify the efficiency of steam engines. And we basically create a parametric Sankey where we can actually, using the system of nodes as inputs and outputs. And the core principle is to kind of conserve mass and energy where the inputs and equals like output in the system. And then also the width of the band actually represents the amount of flow that goes in and out of the system. And by positioning and the direction of the volumes and layering and plays important roles in this representing of understanding of flows in the city. And this tool actually allows these parameters to be configured, enabling a degree of interactivity to explore different spatial conditions of flows. It's almost like a mapping where this approach offers a new perspective on urbanism, reimagining the city through the lens of material flows. And this context, this is a zoom in of it. And then this was actually tested in the studio, circular studio in Seoul, on this building in the neighborhood. This building is called Seonsanga, which is a 1 kilometer long brutalist structure that was built in 1960s. And this became kind of our catalyst to deploy this tool for design process. And here you can see the current situation of this building. And also what is interesting about, this is the first kind of a multi-complex building in Seoul where there's like a residential on the top and the commercial on the bottom and different offices in between and shops in the floor, on the ground floor. And then what is interesting is like around this building, this is where all the manufacturing in the city started to occur. So you can see different clusters of different specific industries that gets built up around this neighborhood, like from building material stores, linings, tool shops, and also like for publishing and also steel processing, woodworking. So a lot of things that happen, that the manufacturing things happen in this area of Seoul. And like there's also like the first open source satellite was built here in this area. And also you can see kind of how it works. Like in order to build something, you kind of have to look at different venues to actually build something together. And this is why this site became interesting for us. And this like different locations became the nodes for the experiments. And here the idea was to turn kind of a city waste into a circular product. And in this process, you can see all these different processes that happens, but also like this process that students embed in as a circular process. So basically they mapped out this kind of a process of turning a waste into a product by this diagram of parametric Sankey. And this you can already see kind of different variations of different projects of how they kind of visually also look like. And this tool actually allows for deploying into the city context, and also actually kind of transforming the dimensions into a 3D as well. So this tool can actually, this tool was also to look in folding the tool from 2D to 3D and then deploying into this building of how these flows can actually, this flows actually how do they adapt in the building. So here's some case, samples of a project that was students' project where they embedded this kind of acupunctural gesture into this building to kind of revive the whole area and by adding the circular process into it. And here you can see kind of a glimpse of the tools that was used in this is kind of obsolete typologies in the building. Here you can see kind of the section throughout the building, but actually this tool expanded further into the machine learning process in this studio where we looked at the artisanal architecture in Kyoto to kind of revitalize the city from kind of a historical city into a circular one. So the process was the same. How we can actually make this process more circular? So students had this kind of different processes that they embedded in to make this process more circular. And the only difference between the previous one and this one is actually the component of kind of using this kind of diagram into creating a 3D models, human interpreted 3D models of different flows. So this process, this actually basically represents the process of this kind of one kind of artisanal work, and then by using this Sankey diagram, we can actually volumetize this flows from these 2D flows. So here you can see kind of the 16 different of 3D flows that was actually transformed into a 3D color printed model to represent different flows, and then how they blend in by combining different processes, and the thickness actually represents different types of, different weights of the flows. And actually the human interpreted diagram became a way to actually use it into machine learning process to optimize the space. So and this time it was only 16 models. So the idea was like, how can we use these 16 models to actually create something that is efficient in terms of how we can actually arrange the space for these kind of artisanship. And then, so that's why we also looking into kind of a formal understanding of these diagrams, and then kind of topological understanding of this diagram of the graph. And here you can see, so with the 16, it's impossible to do some kind of experiment. So basically, what we did is we dissected the whole models into around the nodes of processes, and then combined them all together to see a holistic view of processes. And we use this as kind of a formal understanding of nodes, and then also, of course, we use the point cloud, and then use the pre-existing models to deploy where these kind of point clouds actually represent are in the space. So we can also cluster these the forms of nodes into different clusters, and so you can kind of identify what kind of different types of formal nodes are there. And also looking at the graph, we can see how the network is, how the processes are connected to each other. So using these two systems, we created this kind of graphs where we can understand how the formal nodes are connected with the processes. And in this process, this is an example of one kind of artisanal project, one project that represents this formal and topological understanding. And we use the obsolete typology again as kind of a way to, like the previous project with the Seonsanga, we used the matcha as kind of our catalyst. And using also basically human in the loop optimize the system to use these two things that we learn from formal understanding and then topological understanding to create different types of options of how we can actually arrange the space in the system. In the building. So here you can see kind of a one optimized of a space configuration, which is actually still yet primitive, because there you can start to understand, you can create a zones where there's a circulation system or structures. So you can go further in terms of optimizing space. This was just basically on 3 floors, and also just a different, arrangement of spaces. So here you can see kind of the example of the student project that actually using this matcha and how they can insert their new project. And this is the last slide, the zoom in of the models, where like some say the form is a concept that has outlived its usefulness and has become frozen and no longer in active development. But I consider form as kind of a specialized token, the models that embodies a wide range of data and information from cultural norms, semantic meanings, human preferences, climate conditions, energy efficiency, and material properties that could help identify innate bonds between tangible form and intangible narratives of data that it incorporates. Thank you.
Frederick, do we have questions from the audience? I'll start.
Yes.
Because there are so many very interesting things that I think will link to the previous talk and discussion that we had. And I will allow myself to try to read below the lines into your first 2 projects that you present, where for me read about against generalization, and therefore the title of the Swissness, right? So you're trying to really capture what is the essence of one particular thing, not only on the archive that you're creating for the competitions, but as well on the object. And my question is precisely on that experiment that you did when defining the forms and then labeling them based on 4 dimensions. I wanted to know if you thought about this as an inverse parametric generative algorithm, where you are trying to learn or trying to revert what was the generation for that model itself. When you have the output, but then you're trying to identify how this output was produced through series of parameters. Will you what will you react if I say that this could be something?
So like basically parametric process versus machine learning process.
Well, I think this is just the inverse.
Yeah.
I'm challenging you,
Yeah.
to
Yeah.
think of this as a inverse parametric genetic algorithm.
Yeah, so what I think is that parametric system was basically you, as an architect, we know what we want. We have the parameters. This is kind of thing that we can actually like imagine. And with the certain parameters, you can actually, that's basically the designing process in the past. And now I feel like by machine learning, we actually have to learn what the machines actually think. So a lot of times in the cases in our teaching studio, we basically would try to figure out what machine sees it and we understand, and then we actually parameterize what machine thinks. So if there's some kind of design element that the image is actually represented, we try to parameterize that again. So it's never like a kind of like a, this is parametric era, this is a machine learning era. We always use all the tools together by using just few images. We still use just few images to actually have a design. So at the end, it's adding kind of another layer of thinking, giving a chance for machines to kind of interpretate what the data actually holds, that what we don't see, because they can pick up on the things that we don't see definitely. And as a human, we also have to critically understand what they are representing. So I think in that question, I think it's still inverse parametric, but I think the thing is, before we defined as architect what the parameter is, but now we can also learn from what the machine thinks as a parameter.
Yeah, this is very interesting if you think about knowledge, because the idea of you bringing meaning to an existing output relates that you are training based on an existing knowledge that you have. So it's embedding sense from your perspective.
Yeah.
And that's what I said about personalization, or the essence of this one thing, instead of doing the generalization of everybody should label these based on these 4 dimensions.
Yes,
and I think this is really interesting to emphasize the idea of personalized models, and how do you embed knowledge, like the human knowledge into.
Yeah, I think that step is quite important, rather than letting just giving everything to machines and then trying to figure out. I think the creation is like one of the important things that we have to do with this machine learning processes. And that's already the design, as you said, yeah.
Any other? Yes.
Very interesting presentation, Frederick. I'm from University of Florida. So you created, like say, using AI, thousands of options in certain forms, right? So that's the advantage of AI. But the next question is, how do we train the AI to optimize those forms or choose a certain form that meets certain criteria? And then ask the AI to help us to understand what is the impact, or what is the effect, or what is the consequences of different forms. So that will help the humans make decisions, or help the AI make better decisions. So this is like 3 steps. First is you create forms, 1,000 forms. Second, you choose the form that meets certain criteria. And third one is optimize that form to the extreme. So any thoughts on that process, or are you working on that? Specifically, you have working on in the Korea case, like using different street form or road form, and what is the consequences of that in terms of traffic flows?
Yeah, so there's a project that we are actually in our lab working on. We call it Blue City Project. It's basically looking at the flows of the city and understanding the city in terms of flow. And one of the aspects is actually what happens if you insert this kind of object or architecture or certain kind of nodes into the system, what could actually happen. So I think the last part that you mentioned is one of the most important part, where what the future is going to look like once you actually implement those forms in it, right? So I think that's something that just came to my mind once you said it, because usually it stops after you design, right? Like it's after form you design, but actually predicting with the machine learning process of how that could impact to the society or the built environment, actually that's quite another aspects of machine learning that is quite important, I think, that could be implemented. I mean, no, it should be implemented, yeah.
Yeah, thanks a lot, Fred, for the presentation. I'm curious about this last project that you showed, how to think about the word form itself. You know, because what I see happening is a kind of concretization of the world of flows, right? So it's a concretization of a topology, a concretization of an infrastructural movement. I'm just wondering, where would the will of the architect be present? You know, if architecture is defined through the flows of data going through it. You know, so it's, I mean, we have this building here, which is a result of this infrastructural optimization. And I'm just curious, how do you see that, and where do you see the role of the architect if it is a purely data-driven process, something like that?
That's a very good question. By these diagrams that we generated of these models, it was quite interesting because students start to understand, like, to talk about their processes or the flows through these diagrams, right? So they can actually, I mean, it makes something that is intangible very tangible. So you start to understand what could be a potential in how these different flows actually affect each other, which we cannot see in the reality. So I think as an architect, it's very important to see this kind of processes, also with the existing context of where the structure goes, where the air flows. So I think we've been using kind of aerodynamic way of thinking in terms of designing spaces or buildings, right? So I think, but now we can actually combine multiple different flows in the building by not just looking at one thing together. I mean, visualizing it, but in terms of calculation, that's another part where we cannot do that. But I think that's this kind of visualizing this kind of model of what you don't see into something physical is something that we can actually communicate between different parties. I mean, just as a representational tool, but also hopefully that actually it impacts the design of, somehow it influences the design. That's the ultimate goal with this project, which a lot of times it was hard for students to actually interpret these diagrammatic flows into an architecture. That step is, I think, was very hard. Yeah, it's basically different than just looking at the programs of the building and putting things are, but now looking at the energy and how people flow, we can kind of specialize the space in a different ways of looking through these diagrams into the architectural design itself.
So I was fascinated by the approach to linguistic description that you took in a few of the projects, and I sort of share that interest. I think in particular, there's what was, I think, clearest as a signal was the linguistic description of a specific static form, and I think it's really useful for creating sort of like comparative maps. It's useful for sort of beginning to sort of understand that territory a little bit more qualitatively. One of the things that is sort of like a corollary to that would be if we have a building or a proposal of one type and we actually want to transform it into something of a different type. I'm curious any thoughts you might have about the description of that transformation, or how we might think of data models, or how we might think of a sort of like data set that allows us to think about those kinds of transformations. Does that make sense?
Like, you mean building transformation in terms of adaptive reuse, or?
Yeah, so what you've kind of created is something like an autocritic, in the sense that you're able to generate some very particular descriptions qualitatively of these projects. I think the next step for an autocritic is to say, well, this project has these kinds of qualities, but what we really want are these different qualities, and in order to get from here to there, we have to go through these series of steps, or this kind of process. And you've touched on process a little bit. I mean, one of your projects actually indicates certain kinds of verbs associated with the project, but I was curious about this almost like meta level model which we might be able to create, which allows the description of those kinds of transformations or operations between models.
Yeah, so I think this is very good. I think that's also the reason why I kind of got so interested in this form, because it's like the representation that actually is an abstract representation that could hold a lot of meaning to it. But if we start to looking at beam, like machine learning a beam, that's going to be a very complex exploration where you cannot grasp that kind of idea very quickly. So the abstraction in terms of representation was very important by choosing the form. So that Swiss architectural competition, the idea is that basically by just inputting the form in it, you will get the qualities, the description of the quality of that project. But then, like, what happens if you start to add different qualities, and then would it have a different forms? So I think this is very interesting and it's also the step towards that I would like to go into by using this language in a more meaningful way than just generating images. I mean, how we can actually generate forms that actually understands the quality of the project. And also there's a lot of data sets out there with the ArcDaily. Every single post with the project can be potentially a data set for understanding the quality of the project. But I feel like there needs to be some kind of a thing that can hold those together to compare different projects together. Not just through images, but something that is, in this case, is basically form for myself. Yeah.
Do you want to react to that?
We just want to follow. Maybe this is more an observation than a question, but I think, one really interesting way, or a sort of like step between qualification and operational or transformational description might be to think about actually the activation maps that are associated with a particular quality, right? So you have an image, for example, or you have a model. You have a quality associated with that, but then there are certain features within the model which are related to that quality. Not everything is relevant to that quality, right? And I wonder if there's some way to sort of relate those specific qualities to the specific maps in a way that you can say, okay, well, if you want to remove this quality, then you need to focus on these particular areas of the project, or if you want to add this quality, these are the areas where you can that you need to concentrate on, almost like localizing the qualities within the model itself. It could be an interesting. It's not at the operational level, but it does give you a hint of where to attend to. I guess.
That's very nice comment. Yeah.
So in a way, my question is totally intended as a follow-up, but kind of connect to this question of language as well, and also questions of translation that Andrew was mentioning before, because what I see through especially the first projects that you were showing us about Swissness and about the Swiss competition system and so on, there's this tension I see in a lot of our work in general between trying to grasp a certain genericness that is meaningful, that can be turned into operationality, it can be activated, can be used, can be queried, can be somehow, can help us understand. And on the other hand, the realization that the specificities are key to that understanding. And that is, of course, and there's awareness of this. And these kind of models and these kind of technologies, kind of in a broad sense, start to allow us that fine grain combined with distant viewing or distant reading, and this is key. However, whatever syntax we might infer using these systems also depend. This is not the key to meaning in a way. They depend on the semantics, and that's when the language comes in as one of the angles of reading this type of data, and how we can try to translate or try to turn one thing into another in a still relevant and coherent way. And I want to point here to the question of foundation models, just because you're mentioning now in your answers to Andrew okay, there's a lot of data sets out there. We should maybe use them. We should maybe train or fine-tune models. And however, we're still in the hands of very, very few, very powerful foundation models that are still key to those translation operations. Clip is one of them. It's like the elephant in the room and these kind of things. And how do you see this? You know, I'd like to hear you on that. Is it because those things are still trained on gigantic common crawl data sets of dubious status, whatever? What do we do with that? Do we embrace this? Do we embrace this kind of internet trash pop culture genericness that is still key to these operations of translations that we still depend on, or do we really need to no? Let's go for like higher quality data. Let's do somehow collegiated effort to try to curate the actual data that will allow us to perform those operations in a meaningful way.
And we also, I mean, the foundation model, we also had this discussion among our team, but foundation models are amazing. It's revolutionary. Like, I mean, bringing all these knowledge into one model, it's so ideal to me. It feels like, but then fine-tuning doesn't work without the foundation model. So you cannot just create a domain-specific knowledge with just that, because it doesn't have rest of the knowledge in it. So I feel like back in the day when we were using GAN, we only focused on this small data set, and that's it, right? But now with the fine-tuning, we can actually, fine-tuning the foundation model, it's another level of using different types of data with this foundation model. So it's not just about image, now it's multi-model, right? So it's like sound and language, but what is important is, I think, is this kind of data interoperability, how the data transforms different models. But again, back to the thing, I think the fine-tuning is, as an architect, I feel like it's, as a designer or someone who wants kind of a specific design intention, I think it's very important. But we cannot underestimate the power of foundation model of mixing the knowledges, I think. So I think that's something we have to kind of operate in between, I feel like, as an architect. Like my foundation model, my fine-tuned model is going to be different than yours fine-tuned model, depending on what kind of architectural agenda that you have. So, but I think using these foundation models is important because it has a power to it. I mean, without this power, it doesn't work. Yeah.
Hi.
Hi.
Thank you for the presentation. Also
Thank
very
you.
interesting. One thing that I might learn again when they upgrade the models, the words and the meanings that the model interprets is sometimes completely different. So how do you think it's happening too fast and they're changing too fast? How can you keep up with this, and how can you, like, every time you have a new model, have to relearn what to say, and the outputs are going to be different.
Yeah, I know. It's like from ChatGPT 4 to ChatGPT 4.0, they have completely different. I mean, not completely different. They have different answers, and I don't know why that happens, but I think at the end it's still us too. We have to define if it's good or not. So I don't see that we can rely everything completely on the knowledge that they produce. We still have to guide the machines to go in a direction that we want it to be. So a lot of times, I don't know if you experience this, like you try to train the ChatGPT 3 to the way you want to think. Have you guys done this sometimes? I don't know if you I direct ChatGPT to say, think like this, okay? Like you have to think like this, and then sometimes it works. So I feel like we still have to guide the machines in a way that.
Very more like for the image generation.
Image generation.
Where you have you put the prompt and we show them the words, and sometimes they just upgrade it and it's completely different. The words are going to come up with different outputs.
Yeah, that's why I like fine-tuning or embedding, because then it's consistent, meaning like.
Even if it upgrades, you think that.
Yeah. I mean, because you have to embed it with the data set that you give them. So, I mean, also different models act differently. So then there's hundreds of different models, so it's not going to be like same. But at the end, it's going to be and then what you get as a kind of if you inverse that process of giving image and then giving the text doesn't completely make sense at all too. So that's why in order to keep the consistency in terms of image generation, you have to know your language. And also I don't know, like from the process that we were teaching the studio, like embedding process was very important to kind of control the concept that you want to generate the images. At least this past experience.
Thank you very much for your presentation. I am a little bit curious about maybe the technical part, which was the logic behind transforming the vectorized models into point clouds that you showed in the first and fourth project?
The first project was mainly about trying to find the right, like what could be available for, I mean, we tested different models, but it was just a decision on kind of using the optimal models. I mean, there was not like a specific reason why we use a point cloud. If there was any other mesh system or I mean, there was also voxel, right? There's a voxel and back then, and what stuck in my mind was this kind of a architectural way of representing the data. And then point cloud was basically it's just points, right? It's the simplest data form, but you can actually arrange the points in a way that you can get something that you might not get out of by just using the typical uniform way of representing the data. So that was just pure speculation. It's going to make a difference. And then by looking at the Tissot, it did make a difference by learning like how the forms were finite, like forms were close to each other. For the last project, there was only 300-400 models of point clouds, right? So it was, I mean, even after dissected. So there was a limitation on using those points to kind of learn the optimal results from machine learning process. So we used the pre-existing model to just put where these points go. So sometimes that's why another case of using kind of a pre-trained model as for architects to kind of using that knowledge to kind of just embed the things that you want to embed to see. That was the second answer for the second project.
Can I ask maybe a simple question? I think you mentioned earlier with the flow to form portion that, you know, with these sort of models of energy that the students sort of struggle to interpret or convert that into architectural proposals. And maybe if you can kind of elaborate, or I'm curious to see what kind of things the students ran into, because it seems to me the model is a sort of, you know, it's a design tool, right?
Yeah.
Ultimately.
Yeah.
And because of the flow to form, that the flow is almost intrinsically a gradient, right?
Yeah.
But then oftentimes we're trying to decide where thresholds are or how to turn the corner, right?
Right.
So that's what I'm curious about. What sort of situations did you encounter?
So I think the step that was missing is actually transforming. Another step that was missing in between the final design and this diagrammatic model was actually transforming this diagram model into a form of the building. That was the part that was missing, and we didn't have time to go through that process. So a lot of time the models was lost in the final stage. But I think that because the tools actually allows to shift the points, shift the nodes, so that nodes could actually be kind of shifted in a way that it could be arranged in the spatial. That's why the machine learning part actually came after the studio. So from that, we can actually kind of shift the nodes in a way that we want, I mean, the optimal in the space. So that process was actually missed in the design studio, which was kind of rethought and then reinforced by this machine learning process. And also like looking at different processes, not just as one single artisanship. By looking at 16 different artisanship, you can see actually some process actually do share same processes.
Yeah.
So you couldn't actually go across just the whole thing. That's why the machine learning actually looked at the whole thing together. So that step was very important that we kind of left it out.
I think we're
Yeah, we're
almost
out.
ready to go.
Yes.
But there is a slightly change of plans. We're gonna go for lunch, and then we're coming back for the last lecture for this panel. Thank you.
Thank you.
If I just have one last statement.
Yes.
Large language English models. That relates a lot with the idea of mapping back what English means to any other culture. I think there is the need to try to describe what exactly that translation means in the way that we speak.
Yeah.
Right?
Agree.
Yeah. Well, thank you so much.
Thank you.